Okay, so in this tutorial we're going to be introducing some of our key ideas about motion. We're going to talk about the difference between distance and displacement, difference between speed and velocity. We're going to look at some distance time graphs. We're going to introduce the equation distance equals speed times time. This equation isn't given, so you need to make sure that you learn this equation for the exams. As always, remember to use the pause button, write down any questions you have as you go through, and write down summary notes. So first of all, let's just check that we understand the difference between distance and displacement. Distance is a scalar quantity. It is a measure of how far an object moves. It doesn't have a direction, only a magnitude, because it's a scalar quantity. Displacement is a vector quantity. It's the distance an object moves, measured in a straight line from the starting point to the finish in a particular direction. So for example, if we went on a journey and we started here and we went around here, then all the way around here and all the way around here and finished here, the distance we travelled might be something like, say, 30 metres, but our displacement would be 1 metre 100 degrees from the north. So we've just said that this is north and that angle there is 100 degrees. It has a magnitude and a direction. Now we can calculate the speed of an object. Speed is scalar, it has magnitude, not direction. And we use this equation here. Distance equals speed times time. We're going to measure distance in metres, speed in metres per second, and time in seconds. If we wrote this in symbols, which is where we have to pay really careful attention, we would use the symbol S for distance and displacement. We would use the symbol V for speed and velocity, and we would use the symbol T for time. So your equation would look like this: S equals VT. You're not given this equation, so it could be distance equals speed times time, or it could be displacement equals velocity times time. So for example, if we look at this worked example, if you're told that you travel a distance of 400 metres in a time of 100 seconds, we can calculate the average speed of that journey. We use our equation, we rearrange it, so we get V equals 400 divided by 100, and that will give us an average speed for the journey of 4 metres per second. When we're talking about the average speed, that means not necessarily that it travelled at 4 metres per second for the entire journey. At some points it would have been travelling faster, and at some points it would have been travelling slower. But if we take the average of the speeds, we get 4 metres per second. We can also use this equation if an object is travelling at a constant speed. So if the speed does not change, if it's constant, then you can use this equation. Now the exam board would like you to know some typical speeds of different things. So, and these we just need to learn. So for example, they're suggesting that the typical speed of somebody walking is 1.5 metres per second. The typical speed of somebody running is 3 metres per second, and the typical speed of somebody cycling is 6 metres per second, and that this varies with age and fitness levels. You also need to know that the speed of sound in air is 330 metres per second. So these speeds need learning and writing down in your notes. Next we're going to talk about velocity. Velocity is a vector quantity that is measured in metres per second, so it's the speed of an object in a given direction. Now what this means is that we can have a situation where if we think about an object travelling in a circle, okay, this object could be travelling at a constant speed of, let's say, 3 metres per second, but because its direction as it travels around the circle is constantly changing, that means its velocity is changing. So you can have situations where an object's speed is constant, but its velocity is constantly changing, because the velocity of an object is the speed of an object in a given direction. It is a vector. Right, next we're going to have a look at distance time graphs. Now when we are looking at graphs in this motion topic, it's really, really important when you see a graph or you're asked to plot a graph in an exam question to first of all have a look at the axes of the graph. Distance time graphs and velocity time graphs are different things. they show different things, they have to be interpreted in a different way. So first job, look at the axes and remind yourself what the graph is showing. So here we've got an example. If an object moves along in a straight line, the distance travelled can be represented by a distance time graph. So here I've got some data about the distance travelled, and here I've got some data about the time travelled. So I'm going to plot time along the x-axis, distance along the y-axis. I plot the points of small neat crosses, and because this is a journey, I'm going to join the dots up with lines rather than have one single line of best fit as we do with other experimental data. Now, depending on the shape of the graph, the gradient of different sections of the graph, we can tell different things. So, for example, if on a distance time graph you have a horizontal line, then the object is stationary and not moving. If you have a straight line that's not horizontal, that suggests that the object is travelling at a constant speed that isn't 0 meters per second. The steeper the line is, the faster the object is travelling. So the gradient is telling us about the speed of the object on a distance time graph. Now these are all straight lines up here, but if you have a look here, we've got some curves. So here we've got a change in gradient, and here we've got a change in gradient, and we need to be able to say what's going on. So here we can see the gradient gets less steep, and remember the gradient tells us the speed, so the speed gets smaller. So when it curves this way, we can say the object is decelerating or slowing down. Whereas in this situation here, the line starts less steep and becomes more steep, so we start with a smaller speed and it turns into a bigger speed. So this object is speeding up or accelerating. So what we're going to look at now is how we can calculate the speed from a distance time graph. And we said that the gradient, the steepness of the graph, tells us the speed. So we're going to find the gradient of different sections of the graph to find the speed. So in order to find the gradient, we need to draw the triangle from 2 points on the line, and you can see between these 2 points it's a straight line with a constant gradient. We then use the scale here and here on the axes to work out the change in the y-axis. So this reading, if you follow it across, is on 2, this reading, if you follow it across, is on 32. So we look for the change in the y-axis, 32 minus 2 equals 30. And we do the same downwards, we follow these dots down. This one's on 5, this one's on 15. So we look for the difference here, so we do 15 minus 5, that gives us 10. And we know that the gradient of a line is the change in y divided by the change in x. So if we put these numbers here into this equation, we get the gradient is equal to 30 over 10, which means our gradient is equal to 3. And we then need to add units to that, because that tells us that the speed is 3 meters per second. Now in some situations you might be asked to find the speed from a distance time graph, but for a section that isn't a straight line. So here we've got an example. So I've sketched a graph and I want to find the speed at this point on the distance time graph, but that's a curve, so I can't find the gradient of the curve. But what I can do is I can draw a tangent to the line here, and I can then find the gradient of that tangent just as I did before. So I draw in my triangle, I find the change in y, I find the change in x, read it off the scales, delta y divided by delta x, that gives me the gradient of the tangent. Now, in order to draw a tangent, what you want is to have a straight line that is angled so that it only touches the graph at the point you're interested in. And we'll practice that a little bit more in lessons. So, to summarise, we know that distance and speed are scalar quantities that only have a magnitude. We know that displacement and velocities are vector quantities, they have a magnitude and a direction. We've been introduced to this equation, distance equals speed times time, with the symbols S for distance and displacement, V for speed or velocity, and T for time. And we're measuring distance in metres, speed in metres per second, and time in seconds. We know that if we were given a distance time graph and it had different shapes, we can then label these different parts. So this section here is a straight line. We know the object's travelling at constant speed. This section here is a horizontal line, so we know the object isn't moving. Then we can see here we've got a curve, the gradient's getting steeper, so we know the object is accelerating. We then have another horizontal section, so we know the object is stationary. And we then have another curve where the gradient decreases, so we know the object is decelerating. Make sure you've got your notes up to date, bring any questions to the next lesson, and let me know if you have any questions.